Okay, does anybody want to come forward? If you have
Yes,
this
sir.
problem a little bit.
I tried the question and I got 3 percentages. Can I say that?
Yes, yes.
So for P is equal to 0.05 and Q is equal to 0.01, I got about
Yes.
32.4%.
Okay,
And
so
uh,
you were looking at this case
yeah,
and you got 32%. Okay.
for for point 1, 51.4%,
51.4%. Okay.
and for point 5, 90.5.
90.5. Okay. That seems a bit off, but
Yeah, yeah,
I could be wrong. I would think that when Q is equal to 0.5,
it should be high.
it should be at least greater than 95%,
Yeah.
because P is equal to 0.05. Okay, does anybody else have similar answers? Okay, if not, then I will show what I got. Let's see. Okay, so this is the result that I got. So you see, when we do just one test and we are looking at P equal to 0.05, the probability that the person has the disease is close to 16%. Right here it is 0.15844. So this yellow line shows the probability when you do just one test, the posterior probability. And the blue line shows the posterior probability when you do 2 consecutive tests. And here you can see that the percentage already shoots up. It becomes close to 78%, 80%. So the answer that you had, which was around 32% or something, maybe that is not the correct answer. Okay. This is for the case when Q is, oh, sorry. This is for the case when Q is equal to 0.5. So maybe I take back my words. No, wait a second. Okay, there is a labeling mistake. This is actually indeed for the case when Q is equal to 0.01. When Q is equal to 0.5, this is the situation. So here again, we want to look at the smaller range and so you see now when Q is equal to 0.5, if you do single test, then the probability that the person has the disease when the test outcome is positive is 95%. And if you do 2 tests, then it becomes 99.7%. If you record positive in both the tests when Q is equal to 0.5, then pretty much certainly you have the disease. And then we can also look at this other case. Again, this yellow dotted line is for the single, the blue solid line is for the case when you do two consecutive tests. And so now we can look at the same thing again here. And yeah, so when Q is 10%, you get about 67% chance if your test came out positive. But if you do repeated tests, then it shoots up to almost 97.5%. Okay, so these are the answers. Okay, so I'm a little bit surprised that nobody else did this. This would have been a good thing to pursue. It would have shown to me that you guys are interested in looking at such problems, and if you have obtained certain understanding, you can expand upon it yourself. So let me ask you this. This lab, the lab number 3, which is the analysis lab I have given to you, that lab is due today. How are things going there? Are you able to make progress, or you haven't been spending too much time on it?
It is complete.
Sorry?
It is complete.
Okay, so then the due date for tonight is fine, right? I can move on with that.
Yes,
Sir,
Yes, sir.
sir, can you,
Okay.
Yes, sir.
sir, can you increase it for tomorrow afternoon if possible? I'm
Tomorrow
facing
possible.
some.
Why
I'm
is that?
I'm facing some issue, like problem with the last question. I'm trying to figure it out, but it's taking me some time.
You won't be able to finish it in the whole day today? If this was an exam, you would be given only 2 hours to solve all the problems. So you won't be able to finish it by midnight today?
Sir, I'll do it. Sorry, I'll do it.
Yeah. Let's continue with today's deadline to tonight midnight. I think you will have to push yourself and think of it as an exam, except that exam having a duration of 2 to 3 days. I mean, this is what happens in the real life also. When you start working, you will have deadline which are not changeable, because the deadline comes from external factors, like maybe the customers of your company will be coming to meet you, and you can't ask them to postpone their visit. So working against the deadline and meeting those deadlines is kind of not a technical skill, but some related skill that you need to pick up. There will always be some pressure on meeting the deadlines. Okay, fine. So let us move forward. So I think this type of charts we had already looked at earlier. Now let us look at the final topic, which is how to quantify the amount of information that is transferred over the communication channel.
Sir, can you teach the previous example, because I was not able to solve it?
I cannot hear you. Kalp, you are speaking?
Yes, sir. Can you teach us how to solve previous example? Because I was not able to solve.
Can I teach you how to solve the previous example? Yes, absolutely. I can teach you, but I would like you to. I mean, okay, so Kalp, you have taken a shot at it and you are not able to solve it, uh, which is fine, but at least you tried. What I would like to see is that the others also try this problem on their own, and then I will show you how to teach, how to solve this. Okay? Uh, I think
Okay.
it's better that you yourself spend some time solving the problem, kind of wrestling with this problem or any problem, and then only the solution is given to you. So if I just give you the solution, then it probably doesn't help your thinking process as much. Okay?
Okay, sir. I will try.
But okay, I think you made a good point. Let me at least give you certain hints how to think about it. So that's a valid point. So I won't give you the whole answer, but let me give you some hint. Okay, so see, this is uh, the problem of repeated tests, right, that we are looking at. But for the repeated case, the person, whether the person has the disease or not, the underlying cause doesn't repeat, right? If person has the disease, x is equal to 1, otherwise x is equal to 0, right? So in terms of the source, it is still binary. Source is still binary. But what about the outcome? What about the observation or the effects? Well, they don't remain binary anymore. How many possibilities you can have when you do two consecutive tests?
4.
4. So let me put 4 circles. And maybe I will. Yes.
Hello.
So these are.
सर आपका स्क्रीन देख नहीं रहा सर
Oh, you are not able
ऐसा
to.
ब्लैक स्क्रीन आ रही है
No, it is
It's
visible.
visible. It is visible.
It's visible, sir.
It is visible, sir.
विजिबल है
Okay, visible or not visible? Because some of you are saying it is not
इट इज
visible.
विजिबल
Sir,
सर
it is visible.
It's visible.
There might be some issue on his end.
Yeah.
Okay, is the issue solved? I have
यस
tried
सर
it again.
यस
Okay, so there are the causes still remain one of two, but in terms of observation, in terms of y,
Am I audible, sir?
yeah,
Sir, I have after the yesterday's class, sir, I have think of the solution, but I have not the screenshot of the problem. But uh, after the beginning of the class, I have tried, sir. I got the right answer.
you solve the problem yourself.
Yes, sir.
Okay, so
In the
what was
0.5 case,
for,
sir,
what was
I have
what
just
was your answer for q equal to 1%?
sir, I have not calculated for that, but I have calculated for 0.5. It's 99.7. I think you have
Okay,
told.
yeah, so 99.7 is the right answer. Then
Sir, I
you
have just taken the prior as a y is equal to prior as probability of means p is equal to x is equal to 1 by y is equal to 1 as a prior for probability of x is equal to 1. Instead of probability of x is equal to 1, I have taken probability of x is equal to 1 by y is equal to. Same for p is equal to x is equal to 0. Instead of p is equal to x is equal to 0, I have taken
Okay, Achyut, what you are saying is not fully understandable by me and maybe by others also. So instead of spending time on that, maybe you can write up what you have done and send it to me. And if it makes sense, I will show it to the class, okay? Next time. But right now, I just want to give you all kind of a way to think about how to solve this problem. So now we are having 4 different possibilities. One is 0, 0, right? This is the case in which the outcome is 0 for both the tests that you take. The other possibility is certainly that in the first test you are negative, the second test you are positive. Or it could be that the first is positive, second is negative, and then the final one is that you are tested positive in both the tests. Right? This makes sense?
Yes, sir.
Okay. So now you draw the same type of diagram that we had, except you will have 4 lines coming from a particular course. This is x equal to 0. And similarly, you will have 4 lines going to each of these outcomes from x equal to 1. Right? Now, what are the probabilities that we give to this x values? These are called the prior probabilities, right? 1 minus q. And this is,
1 minus q1.
so this is same as before, no change. But what about these lines? What are the probabilities that we give to these lines? What are we calling them, first of all?
Likelihood.
Likelihood, correct. Likelihood. We can even call it function, actually. It's actually probability, but probability mass function, but it's shortly called, briefly called as likelihood function. So now who can tell me what likelihood should I give to this first line? Remember, if it was just the simple BSc case, this first line was given likelihood of 1 minus p. And then we had only one more line, which was this line, and its likelihood was p.
सर ऊपर वाली को 1 माइनस पी दे दीजिए और नीचे तीनों को p/3.
ऊपर वाली को 1 minus p दे दीजिए और नीचे को
तीनों को p/3.
no.
No.
Sorry?
Square. 1 minus p square.
Exactly. Who said 1 minus p squared?
Path.
Okay. So 1 minus p squared is the right answer, and the reason is because you are taking 2 tests, one after another. And you have no reason to believe that this two different tests are kind of going to be correlated or going to be dependent on each other. You can assume that the outcomes are independent, right? And so we have already seen the definition of independence, how it translates to probabilities. When 2 events are independent, their probabilities multiply. And so therefore, the probability of individual event 0 is 1 minus p, and another 0 is another 1 minus p. They multiply, and so you get 1 minus p squared. What about the second line now?
1 minus p into p.
Into 1
Exactly.
minus
It should
p.
be 1 minus p times p. The third line should also be
1
same.
minus p.
Times p, because it's also you're getting one test positive, another test negative. And then finally,
P square.
P square.
p squared. Now, if you have a doubt whether what you did your calculation that you did, whether it is correct or not, remember that this is the conditional PMF. Conditional PMF of Y is 4 possibilities of Y when the cause is 0. Now, all the PMFs have to add up to 1. So if you want to verify whether this calculation is correct or not, you can add these 4 values and see whether they turn out to be 1. And they should turn out to be 1. If you expand all these expressions and then just add them up, you will see that everything cancels out except there will be just 1 remaining, which shows that these values are correct. Same thing you can do for these bottom 4 lines. They have the same expressions. And so now all the all the mathematical expressions are now with you. All you have to do is, the problem that was being asked to you was that you are sitting at this particular node. Both your tests have come out positive. And so now you are going backward. Remember, like what we had. You're going towards x equal to 0 and x equal to 1. So that is what you need to do to solve this problem. Okay, this makes sense? Yes, no?
Yes, sir.
Yes, sir.
Okay. So
Yes, sir.
you may be that, okay, fine, this is all good. It's maybe interesting to some of you that, especially in today's times, where a lot of people are suffering from this disease. And it's not only that, somebody is having the disease or somebody is going and doing the test. It's very much possible that many of you may have woken up today and maybe feeling some sore throat or maybe having even some temperature. And you are wondering whether it is because of coronavirus or because of common cold. And so this problem is interesting in that sense, interesting in its own right. It's interesting because this type of problems, and we saw, right? We looked at multiple examples of real life where we saw whether if some car alarm goes up at night, what do we say? Whether somebody is trying to steal our car or not? And many such examples that we have seen. So this type of graphical framework that we have looked at in context of Bayesian estimation is very much relevant for the day-to-day life, what our brains do all the time. But this has two significance. This is not just for fun, or this is not just for thinking about real life situation. It actually drives a lot of what you will do as an ICT engineer. How in two different ways. One is those of you who get interested in machine learning. This entire framework that we are putting forward right now is one of the key element of machine learning. When we say machine learning, when we say machine intelligence or artificial intelligence, what are we trying to do? We are trying to take computer and we are trying to give intelligence to it. Now, computer by itself doesn't have intelligence. But if computer can start thinking in terms of such beliefs, and if computer can be given certain data, and using the data, if it can form beliefs and update the beliefs, then you see what I've been trying to emphasize repeatedly, that this is what we do all the time, what our brains do all the time. And it is because our brains are continuously updating the beliefs is a large reason why we are actually considered as intelligent beings. And so for computers also to be called intelligent, one central aspect that they have to be able to do is this type of belief updates. And so therefore, all of this that we are looking at right now, it is not confined only to CT111. This becomes the bedrock, this becomes kind of the foundation of a central pillar of machine learning and artificial intelligence. So this is important in that sense. Now, this specific example that I gave you, where you go and do two different tests, why is that important in a practical sense? Well, now I will go to the specific topic of CT111. And I will show to you that just the way that we saw earlier that the problem of somebody doing a single test is directly maps to a binary symmetric channel, which is one of the key models of a communication system. This particular problem of real life is also directly applicable to one of the key design concept of communication system, which is called channel coding. So what is that channel coding? What does it do? All of that is we will be looking at later on in this course. But that topic of channel coding, what is also known as forward error correction coding, is motivated by this example. Actually, one of the techniques of channel coding directly is this technique that we are looking at. So this is not some problem that I gave you to just keep you busy. This is very relevant. It directly maps to something, some particular technology and a skill set, some skills that you will be learning out of this course. So there is that connection here that I wanted to mention now, but we will be actually bringing out that connection later on in the class.
Hello, sir.
Yes, go ahead.
Sir, in that example, I have thought different method. Sir, we will first we will consider only first test case, and after that we will update Q likewise, and we will use that updated Q in for second test.
Absolutely,
So,
that is excellent. So who is speaking? Vandan?
yes, sir.
So Vandan,
Sir, I have also calculated in that manner.
okay, that is an excellent.
Prior will be changed. That was what I am trying to say.
Okay, that is an excellent thought process. In fact, what you will see is that any sufficiently nice problem, okay, if a problem is nice, and by nice I mean it makes you think deeply. There are some problems which are superficial, so they don't belong to this nice category. But if a problem is interesting enough so that it makes you wonder about how to kind of understand the underlying question, then you will find that the same question can be solved in multiple different ways. This particular way that I have described is just one way. What you are describing is another way. And what you are describing is actually very, very nice way, in fact. And we will be actually going into that particular topic later in this semester, and it is called, I'll write it here. It's called Bayesian belief propagation. Okay, so what you're describing, it can be called as propagating your belief. you are forming one belief using one measurement, and then that belief you are going and taking it to updating your beliefs when you get the second measurement. So you are sequentially propagating your belief. And this scheme of belief propagation, BP in short, is an extremely crucial technique, both in machine learning as well as in communication systems. So, excellent point. Good point. What I suggest is you solve the problem both the ways and make sure that you get the same answer. You use this direct way that I'm describing here, and you use this way in which you sequentially update your beliefs. And the mathematical answer, the formulas that you get should be identical. Very good point.
Sir, only Y will be only two possibilities. No, that second is positive or a negative.
If you do sequential updates, or if you do this Bayesian belief propagation, which is what I understand you were doing, then at a time you have only two possibilities, y is equal to 0 or 1.
Okay.
To the first test, you have two possibilities, 0 or 1. And then using that, you update your prior. That updated prior now becomes the prior for the next test. And then now again, you look at the outcome of the second test and update the prior one more time.
Okay.
Okay, good. So give it a shot. And by the way, this is the problem that I'll be asking to you in this new lab that I'll be giving by tomorrow. And this lab also will be completely analytical. But I think a lot of it is going to be this problem. Okay. Okay, so now we are moving on to the topic of answering the question regarding the information transfer through these type of channels. Right now we are looking only at binary symmetric channel or BSC, but we will see there are other channel models as well that we will be looking at. So you see that in answering the question of how to measure the information that is generated by the source, we derived this concept of entropy of the source. And we said that entropy can be kind of thought of as the temperature. Let's say temperature of a gas which is in a closed container. So the question is now that in this type of framework where source is taking a certain value, person has the disease or doesn't have the disease, a communication transmitter either sends x equal to 0 or x equal to 1. But we don't actually observe that directly. We observe it through some evidence or some effect. And that effect we have called y. So y is 0 or 1 in this disease problem. So the question is, what is the entropy of the source after we obtain a particular evidence? So that is a very interesting question. And the way I would like you to think about it is, remember that we had mentioned this last time. This was one of the observations that we had, that the source, or specifically the PMF of the source, ends up being very different, whether we get y equal to 1 or y equal to 0. So if you are tested positive, then you are really worried. If you're tested negative, then you can breathe a sigh of relief. Essentially, what is happening is that your beliefs regarding the source are changing, depending on whether you get the test outcome y equal to 0 or whether you get y equal to 1. So that is one thing that you should keep in mind. Now, given that, if you look at this question, that what is the entropy of the source after we obtain a particular evidence, then one thing that we can say right away is that it depends, right? It depends whether we got, depends on if y is equal to 1 or y is equal to 0. The posterior, if y equal to 1, the parameter changes from q to q prime. Remember, this q prime is the notation that we introduced last time. And we say that for the diseased case, the q was 0.01. And then after the test came out positive, it became 0.16. Right? But if y is equal to 0, q changes from q to q double prime. Q is still 0.0, q is still 1%. But if your test turns out negative, then this becomes very small. If test turns out negative, it becomes maybe 0.0001 or something. Whereas if the test turns out positive, yeah, maybe this will become a little larger. So, so these are the two cases. When test is positive, Q becomes a little larger. From 1%, it becomes 16%. If the test turns out negative, then Q becomes very small, maybe 0.001%. So the source starts behaving either as Q prime, a Bernoulli Q prime source, if we get y equal to 1, or it starts behaving as Bernoulli Q double prime source, if y is equal to 0. Does this make sense to you?
Yes, sir.
Yes.
This is what we were doing actually yesterday when we were looking at all these charts. This lambda 1 and lambda 0 are nothing but, lambda 1 is nothing but q prime divided by 1 minus q prime. And lambda 0 is nothing but 1 minus q double prime divided by q double prime. And you can see from this that because lambda 1 and lambda 0 are different for a given value of p, q prime and q double prime are also going to be different. But regardless, I would say that the source, which was this source, so this is always going to be x equal to 0. This is going to be x equal to 1 line. So this is our prior. And in this case, this was 1 minus q, and this was q. If we get y equal to 1, then this becomes 1 minus q prime, and this becomes q prime. And if we get y equal to 0, then this becomes 1 minus q double prime, and this becomes q double prime. So the answer to this question is, it depends on whether we get y equal to 1 or y equal to 0. If we got y equal to 1, then what will be the entropy of the source?
Sir, it can be as we did in Bernoulli.
What will be the entropy of the source if y is equal to 1?
Or 1 minus q
Will
given
it be
as
summation?
Log base to 1 minus q prime again summation.
Yes.
Yes, yes. So it will be same the entropy formula for the binary source, except q will be replaced by q prime. And what will be the entropy of the source if y is equal to 0? In that case, q will be replaced by q double prime. So this is called the conditional entropy of the source after we obtain a particular evidence. And this is the notation for it. This conditional entropy is written as h of x given by. And the formula remains very much similar. But before we get into the exact formula, let me mention that, remember, this was the entropy before we got any, before we made any measurement. And this is the entropy of the source after we obtain a particular measurement. And remember, the way we are thinking of source is like atoms vibrating in a closed container. So this is now the really very elegant, very nice way of defining the information that we are getting. And that has to do with this notion of conditional entropy. What is the entropy of the source after you get a particular measurement? Specifically, if the entropy of the source reduces, if it goes down after you get the measurement, then what this Bayesian framework tells us is that then you can say that you have been informed. So if h of x, the entropy of the source before you got the measurement, is same as the entropy of the source after you got the measurement, conditional entropy x given y, then we can say that no information got transferred. Does this make sense to you?
Yes.
Because you see, what we are trying to do in a communication system is at the receiver side, we want to know exactly what outcome the source had. Suppose if we knew exactly with 100% belief, with 100% probability, the outcome that source had, then what will become to this conditional entropy?
It becomes zero, sir.
Sorry?
Zero.
It
It
will
will become
become zero
zero. Exactly. Very good. So
because
if
the information disappears of the source.
if we knew after getting y, let's say that after I go and take the test and the test comes out positive, if I can be 100% sure that I have the disease, then I don't have any uncertainty remaining in terms of my disease status anymore. So the conditional entropy becomes zero. that is the best type of test that you can ever take. But today morning, if you woke up and maybe you had some runny nose or sore throat, now you are wondering whether you have this coronavirus or not. And maybe your mom is saying, oh my God, I'm so worried. Maybe you have coronavirus. But you will say, no, maybe it is just regular cold. Basically, what is happening is conditional entropy is not zero. Your mommy thinks that, oh, maybe it is coronavirus because she's very worried about you. But you answer back that, oh, there is still a chance that it's just a regular fever. So you are still uncertain. Even after getting this particular symptom, you are still uncertain. In that case, conditional entropy is not zero. Okay, so for the best type of information transfer, this conditional entropy becomes zero after you get a particular measurement. Whereas in reality, because this test will have this P value, right? P is that crossover probability, and P is typically never zero. And so therefore, this conditional entropy also will not be zero after you get a measurement. That is what we saw here only. Conditional entropy won't be zero if this becomes 0.16, or even Q prime is much smaller than 1%, but Q prime is still not zero. So let us now move forward. This is the way to define conditional entropy. It is exactly the same definition as before, except all the probabilities are replaced by the conditional probabilities. So when suppose y is equal to 0, then this will be q double prime, and this will also be q double prime. Or if y is equal to 1, then this will be q prime, and this also will be q prime. So this is the exact same formula as before, except we are replacing the probabilities by the conditional probabilities given a particular measurement. And then now we have two different conditional entropies. And so we have to do an average of these two. Basically, we have to take expectation of those conditional entropies. And this part here is doing that averaging. This here is the same, those two same conditional probabilities. And then here we are doing the expectation, or we are taking the mean value or the expected value by multiplying by the probability that you get a particular test measurement. So this is the final definition of conditional entropy. So with this definition, now we are going to define the information transfer. Any guess in terms of what will be the definition of the information that got transferred over this channel? Can you say that this x given y, this conditional entropy, this itself tells us the amount of information transferred by which information got transferred? Would this be correct statement?
Wouldn't it be the average informativeness of the source after after we observed the evidence?
Yeah, this is the average temperature after you make measurement. Average is taken over all the possible measurements that you can take.
Information is transferred.
So the way to answer this question of how much information is transferred is to go back to this case. This conditional entropy, we said, becomes zero in the best case. If you get the best possible information, so that all your uncertainty about what the source is doing goes away, conditional entropy becomes zero. That is the best case. In this case, you can say that the information transfer was the maximum. And so this conditional entropy cannot be the measure of information transfer. Because in the best case, this conditional entropy becomes zero. So when intuitively you would say that you're getting the maximum information, this conditional entropy gives you an answer which is zero. So conditional entropy by itself is not the right metric. It's not the right parameter to define how much information is getting transferred. But then what would be the right parameter? And you would want to think of in terms of the source temperature before and after you got measurement. Anyone wants to give their thoughts? Yes, go ahead. No? Okay, so the definition of how much information actually gets transferred over communication channel is a function of both the entropy of the source based on prior probabilities and the conditional entropy of the source based on the conditional probabilities. And this okay, Saurav, can you mute yourself? There is some echo disturbance. Okay, thank you. So this was the average temperature of the source before making any measurement. And this is the average temperature of the source after you get the measurement. And the amount of information that gets transferred is equal to the amount by which the average temperature of the source reduces. Not what the average temperature of the source is after you get particular measurement or particular observation, but by how much it reduces compared to h of x. And so when you get a particular message, the information conveyed by that message becomes this: h of x minus the conditional entropy of x given y is equal to j. And the overall information that you get on average is just the difference of these two entropies, h of x minus h of x given y. So this is a very nice way to capture the notion of information as it gets transferred over a communication channel. So let us now take a look at this. Okay, are you able to see my Excel spreadsheet?
Yes.
Yes, sir.
Yes, sir.
Yes.
Okay, so I'm considering the same disease problem, right? So this is the likelihood function, and this is controlled by this parameter P. P is 5%. This is the prior on X. It's controlled by the parameter Q here. And this Q I have set it to be 1%. And so these are the values that are given to us. Right? X is equal to 0, the probability is 99%, X equal to 1, probability is 1%. When X is equal to 0, what is the probability that test comes out positive? 95%. When X is equal to 1, what is the probability that the test still comes out negative? It's only 5%. So this is exactly the problem that we were looking at. Okay, so now let us look at the next 3 lines. This here calculates the joint probabilities. Remember, joint probability is nothing but the product of the conditional times the prior. And so therefore, this is just the product of C column and D column. This is the joint probability. Similarly, joint probability for this case 1, 0 is C5 times D5. So it becomes very small, 0.0005. This is the joint probability. What about the probability that y is equal to 0? Well, y is equal to 0 only in these 2 cases. And therefore, we can apply the rule of marginalization, where we add up the corresponding joint probabilities. And so probability that y is equal to 0 is given by summing these 2 values. And so you get, this is the probability of y equal to 0. And therefore, now you can take the conditional probability of x given y by just dividing E4 with F4. And here you would divide E5 with F5. So this is the posterior. Remember, this 0.001 is what we have called Q double prime. When you get negative test, what is the probability that the source is 1? That probability is 0.001. This is Q. This is Q double prime. Right? Now, what do you think has happened to the conditional entropy? Do you think conditional entropy in this case when y was 0, do you think it would have gone up or gone down compared to the unconditional entropy h of x?
Go down.
Go down, correct. Who said that?
Path.
Why do you think path is gone down?
Because uncertainty becomes lower.
Exactly. We are more certain about whether we have the disease or not. Uncertainty has become smaller. Excellent. And so that is what the remaining columns are going to tell us. This is the entropy of the source. Here I wrote some binary entropy function. It is doing just that negative q times log base 2 of q, negative 1 minus q times log base 2 of 1 minus q. Okay, I wrote a Visual Basic macro for this. So it is doing just that. And it is taking these 2 values at its input. And based on that, it is telling me that the entropy of the source is 0.08 bit. The conditional entropy of the source, as it was just now mentioned, has gone down. From 0.08, it became 0.00655. How did I get that? I took these two values, q prime and 1 minus, q double prime and 1 minus q double prime. And then this is the answer that I got. And so therefore, in this case, we can say that we did get some information transferred. From 0.08, it became 0.006. And so the amount of information transfer is the difference between the two. And it turns out to be 0.074. Okay. Now let us look at the other case when somebody gets tested positive. So this is the other case. The test outcome is positive. The cause can still be 0 or 1. So we go through the same math as before and we find out that the posterior has become this. This is now Q prime. Q prime is now 16%. But you see now an interesting thing happens, right? Previously you were not too much unsure. You had only 1% belief that a person can have disease. But after your test came out positive, that belief shot up. It became 16%. So compared to this case, obviously this source is more uncertain. 99% and 1% is pretty good. You are more or less certain. If it is 84% and 16%, then no, not as much anymore. And so therefore you will see that the conditional entropy actually went up. After you got y equal to 1, the entropy from 0.08 bit, it became 0.63 bit. And so actually this is a case where the information that got transferred was negative. Now, generally you don't want to deal with this type of situation where information is negative, because then what's the point of communicating? When you are communicating, you want information to be always getting transferred in a positive sense. What has been proven by mathematicians is that it can happen that the conditional information can indeed become negative, like what we saw here, but the average information is always going to be positive, no matter what. Either it will be 0 or it will be positive. So this is the average of the two. Here I'm doing the average entropy, right? I'm taking the conditional entropy and multiplying by the corresponding value of y, and then just adding them up so that this is the average and conditional entropy. And compared to the original entropy, it went down. And this is now the absolute amount of information that gets transferred, 0.03 bits. Okay, so this is the way to start thinking about the information transfer that is happening on a binary symmetric channel. Let us experiment.
Excuse me, sir.
Yes.
So can you just repeat these bits one, like 0.03 bits, that part?
Yeah, so the way I got 0.037 is I took the difference between the entropy, h of x, and the average conditional entropy, which is h of x given y. So that is the difference that I'm taking. That becomes 0.03. How did I get this 0.04? I took average of these two conditional probabilities. on average, what is my conditional entropy? This tells me what is the this 0.00655 tells me what is the conditional entropy only if I receive y equal to 0. This tells me the conditional entropy only in the case that y is equal to 1. But at a communication receiver, you are continuously going to get zeros and ones at the receiver. So if you take an average over all the bits that you are getting at the receiver, then this is the conditional entropy overall. It's an average calculated using these 4 highlighted boxes. Okay? Make sense?
Yes, sir.
So let us experiment now. I'm going to turn the prior into 50-50%. 50%, 50%. So I'm not assuming that one case is any more likely than the other. When I turn prior to 50%, what do you think will happen to this h of x?
Increases.
What will be the value?
It would one. It would be one.
It will be 1 bit. Yes. It will take its maximum value of 1 bit. So you see it became 1 bit. Now in this case, for both the cases, whether you get y equal to 0 or y equal to 1, you get exactly the same amount of information, which is 0.7136 bits. And therefore, the average information that you get is also 0.71 bit. So what does it mean? The source is generating 1 bit of information. But at the receiver, you are only getting 0.71 bit out. The rest of 0.28 bits is getting lost. Why is it getting lost? Because the channel is uncertain. So you say that, okay, what if I want to reduce the amount of information that is getting lost? What if I want to increase this information that I'm getting? Well, then one way is to come up with a test which is more accurate. So a test which has 5% error is not as accurate as a test which has only 1% error. If I make this small p equal to 1%, what do you think will happen? Let's just look at it. You see now
entropy will decrease.
conditional entropy reduced. Exactly.
Yes.
And therefore the amount of information that is getting transferred went up. From 0.71 bit, it became 0.91 bit. You are able to send more and more fraction of a bit through the channel. If I make this extremely small, let's say I make it this small, meaning that somebody has come up with a test which is very, very accurate, then you see that I'm transmitting 1 bit of information and I get almost 1 bit out. This is happening because look at what is happening to Q prime and Q double prime. They both are pretty much becoming, Q double prime is pretty much becoming 0 and Q prime is pretty much becoming 1. Which makes sense. This test is so accurate that if you get 0, you can be almost certain that you don't have the disease. Whereas if you get a 1, then you have to be almost certain that you have the disease. So this test is highly accurate, and so you get the corresponding answer. You are able to transfer pretty much the entire amount of information that is being generated by the information source. And that is the amount of information that goes through. So basically, you can think of this communication channel as sort of like a bottle. And this has the tank, overhead tank. How much water flows through from the tank when it comes out of the faucet at your wash basin is going to be determined by whether the channel has this much opening or it is very wide. This is one of the best cases where the pipe is big and thick, and so every bit that you send, pretty much the entire bit comes out. What the case that we were looking at before, 5% case, is not so nice. The pipe now has a lot of dirt, so the amount of water that can flow through has reduced. Almost 0.28 part of the one gets obstructed. You can't do anything about it. And the only fraction that you can get at the receiver successfully is only 71% of a bit. So the last thing for today is, what do you think I should do to this P value here, the one which is highlighted? What should I do to this P value so that this becomes zero? Basically, no information gets transmitted.
0.5.
Worst type of channel possible. And so what do you think that corresponding value of P should be?
0.5. 0.5.
Exactly, it should be 0.5. In this case, information transfer becomes zero. And you can see why it became zero, because the prior was half, 0.5, 0.5, and the posterior is also 0.5, 0.5. So when you get either zero or whether you get one, it doesn't help you at all. Probabilistically, you are not able to update your belief about what the source outcome is. Okay, so this is where we will end today. I hope that this mathematics is clear to you, but if it is not, then I wouldn't worry too much about